Hi everyone, I'm Tiao Li, and my teammates are Si Yuan and Ziyang Xu. In this video, we will give a brief presentation about our final project. The topic of our project is a comparison of the FBCCA and CNN performance in SSVEP-based BCI. Here is the outline of our presentation, and I will cover the first two parts. BCI refers to brain-computer interface. It's a direct communication pathway between a brain and a computer or external device. The aim of BCI studies is to create or establish a non-muscular communication channel for people with severe motor disability to better communication. According to this definition, we need to find a reliable brain signal that can encode the information that patients want to convey or their commands. One of the most commonly used brain signal is the steady-state visual evoked potential, which terms as SSVEP. SSVEP is a brain signal that, in response to a flickering visual stimulus, is mainly produced in the visual cortex. There are several reasons of using SSVEP to drive the BCI systems. Firstly, SSVEP can be recorded by several non-invasive recording electrodes. This means that you don't need to worry about the implantation and the longevity of the electrode. Besides, SSVEP is well known for its high signal-to-noise ratio, and it's less likely for SSVEP signals to be influenced by the artifacts. These are the good things for signal processing. Most importantly, the frequency of SSVEP signals always fixed to the frequency of visual stimuli. In other words, SSVEP is an appropriate signal to store the frequency information and used as an input of BCI system. Here is the simplified diagram of human visual system. There are two main visual pathways shown by the red and blue lines in this diagram. One is the magnocellular pathways shown in red line. This is sensitive to the depth, location, motion, or luminous information. Another is the parvocellular pathway, which is shown by the blue lines in this diagram. The PC pathway is sensitive to color, so the contribution of different pathways to SSVEP generation depends on the stimuli. For example, isoluminant chromatic red or green signals will primarily stimulate the PC pathways, while the 100% luminance contrast signals will stimulate both PC and MC pathways.
So in our project, we want to investigate three main problems. First is that can CNN and FBCCA be operational under limited dataset? We want to understand how much data is actually feasible for both of the algorithm. And secondly, can FBCC and CNN be an universal model? That means if we can train FBCC and CNN using existing database or existing collected data from the existing users, can we use such model to predict users that haven't been seen by the model before? What is the performance of it? And also, we want to investigate the performance and compare the FBCC and CNN in SSVEP-based BCI in terms of prediction accuracy. Before we jump into describing our algorithm, it is a good time for us to really understand what the database that we're using is. So basically, we're using an open source database from Tsinghua University. It contains of 35 participants. The male and to female ratio is 18 to 17. And the total number of targets that you're using is 40. So it's basically 40 flickering signs. And the flickering frequency is ranging from 8 to 15.8 hertz with 0.2 hertz as interval. And there are 6 trials per participant. In their dataset, it describes it as 6 blocks. The stimulation duration for such experiment is 5 seconds. And the total channel that you're using is a 64-channel EEG. However, they're only focusing at 9 channels because those are in the visual cortex. And the sampling frequency is 250 hertz. The bandpass filter that we are using is 0.15 hertz to 200 hertz to incorporate as much information as possible. And also we applied a notch filter at 50 hertz to remove the interference of the power grid. And besides of different frequencies for each of the targets, the phase of that flickering effect is also different. This is mainly due to the synchronous of your visual cortex responses after seeing the flickering sign. Now let's discuss about CNN, which is we proposed a convolutional neural network. The basic training pipeline is as shown in this flowchart, where the raw training data first go to a Fourier transform because we want to analyze the frequency component out of the data. Remember, FSVP requires the people to look at flickering signs, where flickering signs has each target has different frequency. So frequency component is actually important to deal with. In this way, as we turns the temporal data into frequency domain, we could have more information for the CNN neural network to learn. And after that, we feed it into CNN neural network as a forward pass. doing a classification prediction, and using the training labels to calculate the loss, and then backpropagate into the CNN to update the internal parameters of the CNN neural network. And for the testing pipeline, it's basically the same, except that it's only doing the forward pass for predictions rather than having a backpropagation to update the internal parameters of the convolutional neural network. And this is the convolutional neural network that we are using. So basically, it consists of 4 convolutional layers and 3 fully connected layers. The batch size that we are choosing is 32, and the approaches that we are training is only 10 approaches. The learning rate is 0.002. The loss function we're using is cross entropy loss. Activation function that we are using is ReLU, and the dropout rate is 0.1. And worth noting that for both of the FBCCA and the CNN, the training data that we're using is logged at 5 seconds, which is 125 samples. So now let's discuss about the FBCCA, and we basically rebuilt this algorithm from the paper that's been published in 2015 from Tsinghua University. FBCCA actually has been considered as one of the gold standards algorithm in SSVEP decoding, mainly due to its robust performance across different people. The FB here is actually subband. Because it's future banked, we actually perform different bandwidths of bandpasses for each of the subband to extract the data out of it. In our case, we only use 2 subbands. And the X is the testing data. The X hat K is actually the template data for the N's subband, and the K's target, so H in here. The template data is actually where you have collected your user data and you take the average for each block, each target. So basically, if we have 4 blocks of the one user's data, we just simply takes the average for the 4 blocks for each individual targets. So that will be your X hat. And YF, which is the reference signal. The reference signal is where what your signal should look like serialically, because your flickering is actually based on the reference frequency, the reference signals. So your reference signals is consisting with all the sines and cosines signals. It's actually a vector. First, based on your fundamental frequency, which is your flickering frequency, all the way up to up to NH's harmonics frequency. This is because your visual cortex responses also contains harmonic signals besides your fundamental frequencies. And your W's. So your W's here is actually the CCA weight, which is a byproduct of the CCA, not byproduct, but the result of the CCA for the N subband and corresponding to the K's target. And the R's is the correlation coefficient after the CCA and correlations. Wn is the weight for every row. So basically, is in here. So your Wn is the weight for each of the row, which is the features you extract. And here we're setting A equals to 1 and B equals to 0. All right, so now we know what the samples means. Let's go through the flowchart or how the FBCCA actually works. So first of all, you have your testing data and you need to have your template data. That's one of the requirements for FBCCA. You need to have a template data before doing anything. All right, so you have your testing data, you bypass it with different subbands. So let's just remember that each of the procedures is actually the same. So let's just focus on subband 1, where you have your subband 1, this X1 is your testing data, and this is your template data after subband 1. And now you're entering the feature extraction phase. Feature extraction phase is described in B, where you need to compare your data with all different sort of combinations. So first, you need to compare it with your reference data. In here, that will give you a correlation coefficient, and you need to compare it with your template data. You need to compare it with your reference data again, but using CCA with one of the components of the W. And so on and so forth. You have basically 5 different features in here. And after that, all your correlation coefficients will be entering with this, basically this equation to extract your row, which is your feature. So for each of the feature extraction step, you will have 1 row. For each of the subband, you will have, let's say you have N subband, in our case it's 2 subband, we'll have 2 rows. And we use the 2 rows entering this Wn's weighting function, and we'll have our final row, basically. And this is the row for because this is your X, right? So you are comparing for all of the 40 different features, the 40 different targets. So for each test, you need to do 40 times of this. So you have 40 rows. After you have your 40 rows, you just chose the maximum row, and the maximum rows as corresponding XK, which is the target, will be the target that you are looking at. So this is basically FBCCA. So in order to address our concerns and questions, as we proposed at the very beginning, we designed these 3 tasks. So for the first task, we want to train a customized model for each of the user individually. So in such a way that we use the first 5 blocks of the data for each of the user as training, or the template data, training for CNN templates for FBCCA, and use the last block of the data for each of the users as testing data, so that in such a way we could, in our case, we have 35 users, so we train 35 models, and then use the last block of the data for each of the users as testing data to have the prediction accuracy evaluation out of it. The second task is that we want to design a semi-universal model. A semi-universal model basically means that we use the first 5 blocks for every of the subject as training or template data. So basically, all 35 users, the first 5 blocks will be as a training data for one single model. And we use that model And we use the last block of every subject's testing data as testing data. In such a way, we could use this one single model and use the testing data for every subject. And this subject has been seen by the model, and we test that one single giant model and have evaluation on each subject. So this is basically a semi-universal model. The third task that we're using is to train a universal model, where we take all 6 blocks from the first 30 subjects as training or template data, and we train that with one giant model for CNN or for FBCCA, and we use the remaining 5 subjects and all of their 6 blocks as the testing data. So the remaining 5 subjects has never been seen by the model. We want to test if the model of CNN or FBCCA is actually suitable for using existing subjects data, and it can still predict the subject that has never been seen before. And we want to evaluate the prediction accuracy for the last 5 subjects. So the result that we're looking at here is, so here this is the task 1's customized models result. From here, we can see that CNN is actually overfitting. The validation average loss is very, very high, well as the training loss is very low. This is a classic overfitting situation. This is mainly due to the limited number of training data we have, since we only have 5 blocks of data for CNN to train, which is definitely not enough. And however, FBCCA in this case actually performs really outstandingly, with an average of 97.57%, the standard deviation 5.72% of the accuracy across different users. Which is really impressive. CNN, on the other hand, only scores at 40.44% accuracy, but that's what we expected, since CNN or neural networks generally requires larger data set to train. And for task 2, we're switching to a semi-universal data. As the data, because we're using all 35 users' first 5 blocks, so compared to task 1, CNN this time actually has 35 times more data to train. And surprisingly, or as expected, also that the prediction accuracy of the CNN increased, and sometimes even outperforms FBCCA in some cases, let's say S8, S21, and S28. However, in general, FBCCA still has a higher prediction accuracy, with a 94.35% plus or minus 10.78% of the accuracy. And the average accuracy of CNN this time is 86.92%, which is substantially increased from 40% in task 1. Which suggests that, well, CNN and FBCCA actually has the potential to be a universal model, because in this way, in semi-universal setting, it can still discriminate with different people's data. So in task 3, we are trying out the universal model setting, where we use the first 30 users' data as training data and the last 5 users' data as testing data. And from here, we can tell that both of the FBCCA and the CNN are capable of doing such tasks, where FBCCA still has a huge leap at 94.33% in accuracy compared to CNN with only 83.18% of accuracy. However, I do suspect that CNN can do even better if we have even more data. In this experiment, we basically wrap up that CNN and FBCCA can be a universal model, and we have enough data. We could use such model to train only once and can provide to anyone's usage or data, which is a huge news or a really good news for commercialization, since universal capability is a key, and it could definitely lower the cost for algorithm design, for software design as well.
Also, our study mainly focused on the algorithms. The data we've got is from Tsinghua University and is recorded based on weight electrodes. However, since weight electrodes require the use of conductive drain or saline solution, which can be very messy and uncomfortable for users, and it needs a lot of preparation to set up. So in real-life application, dry electrodes can be a better choice. Currently, dry electrodes have lower signal quality compared to weight electrodes, as they do not provide as low impedance contact with the skin. So dry electrodes with high accuracy is one future direction for research. And since EEG can be easily affected by other signals, such as motion artifacts, so improved recording equipments and other noise removal techniques are expected. The single frequency paradigm is applied in this study, and as is frequently used in EEG-based brain-machine interface systems. However, there has been growing interest in using dual or multiple frequency paradigm in BCI systems to improve accuracy and robustness. Dual or multiple frequency paradigms involve presenting visual stimuli that flicker at multiple frequencies simultaneously, and analyzing the resulting SSVEP response using advanced signal processing techniques. By presenting stimuli in different frequencies, these paradigms can increase the number of targets that a user can select, allowing for more complex control of a BCI system. One example of dual frequency paradigm is harmonic targeting approach, which can improve the accuracy of SSVEP detection by using harmonic relation between the frequencies to enhance the signal-to-noise ratio to the recording EEG signals. And as you can see in previous slides, the CNN model is overfitting in task 1 and task 2. In future studies, more data can be applied into the training to generate a more universal deep learning-based SSVEP model. And improving communication speed of BCIs is a critical issue for various applications, including BCI spillers. To the best of our knowledge, the online information transfer rates of more than 300 bits per minute is the highest speeds reported in EEG-based BCI studies. This should be one of the performance considerations when studying the paradigms. Okay, this is our reference of these slides. So thank you, that's all.